Hi, this is Hong. This is machine learning from concept to code. The way we're going to approach everything we learn in machine learning for me is to start from the concept, and then we're going to follow by the coding part. This is going to help you to truly appreciate the execution part of machine learning. Today's topic is gradient descent algorithm. First, we'll start with the concept, and let's go back about 170 years ago. In 1847, Louis Cauchy proposed gradient descent algorithm. Gradient means slope and descent means steepest. So this is the first order iterative optimization algorithm. This is a mouthful phrase, but I'm going to break this down for you. What is a first order algorithm? A first order algorithm is an algorithm that's going to approximate based on a linear function. In linear algebra, linear function means it's a function that maps the two vector space and preserves the additions and scalar multiplications. As you can see here, you have two vector x plus y. If we sum them up and then do the operation on them and we get a result, that result will be exactly equal to if we transform x on its own, transform y on its own, and do the sum of the transformation result. The second one is scalar multiplication, so we have f of ax equal to af of x. So that is a linear function. First order algorithm is an algorithm that approximates based on linear function. Iterative is a step-by-step algorithm, starting with the first value, which is a guess. So the first guess going to lead to the second guess, lead to the next guess. An optimization algorithm meaning we're going to optimize something, make something as best as possible. Now, going back to machine learning objective, it's always about classifying. Okay, we're talking about classification algorithm here. The objective of classifications algorithm is to be able to be as accurate as possible when it comes to classify, identify different objects belonging to different class. And we call those object data points, our samples, right? So we call objective functions to measure the performance of the classifiers during training. And the common form of objective function is the cost function. The cost function simply explains the difference between expected class, expected label, and actual label, predicted label. So when we say the true label, the actual label, or expected label are meaning exact same thing. So today we'll look in particular to the cost function of ADLINE, stand for adaptive linear neuron. So here's its cost function. It looks complicated, but it's not. Let me break it down for you. When you see I here, it's mean the I data point. We could use the true class of data point I, subtract by the net input of data point I, which is a dot product between two vector x and w. Watch my other videos about data representations and the dot product. And we're going to square the difference, sum them all up, and divide the sum by 2. Then, divided by 2 here simply, it's just for convenience. So why do we do that? Because we know to find the minima or maxima, we need to take the derivative of the function. So just to refresh us about taking the derivative of a function. So if we have a function square, we take the derivative of that function, it's going to be equal to 2 multiplied by the same function and multiplied by the derivative of that function. So now we're going to take the partial derivative and based on the component of the weight. So let's recall that our data set for each data point, we will have D feature. And the weight factors will be able to accommodate those D features plus a bias value. So what it means is, let's take a look into taking the derivative of JW. Don't be scared of this long equation. We're going to go from left to right. First, we're going to replace the derivative of JW by the function itself. Okay. Next, we're going to plug in using the derivative formula, where you move 2 to the beginning, multiply by f, which is this function here, and multiply by its derivative. Now, its derivative here this is a multivariate function, so you have d, okay, d features plus a bias. Then we will have to take care of each part of the features. So this one is, we're looking to the derivative of feature j, for j starting from 1 to d plus 1. The one part is bias. Because we take the derivative by the weight factor of feature j, every other part of x and y will become 0. The only thing we're actually going to be able to stay is the j feature of the I data point. We sum it all up. Okay? Alright. Now, when we update the weight of feature j, we make sure that we multiply the change of jw with negative eta, because we want to find the minimum. And then we get the formula here exactly match what we already calculated as a derivative of jw in correspondent with the j component of vector w. Let's take a look into these animations. What I want to show here is that gradient descent is to move, okay, we're going to make a guess, and moving from other part of the cost function, in this case is a parabola for our visualization, going downward toward the minimum. So w has to move toward 0 in this case, and the cost is going to go down from the y-axis. If we want to know more about this particular moving downward, we have to go back to refresh on calculus when we look into the slope to be equal to the difference between the previous step and the next step. Okay, the previous locations and the new locations. So change in y over the change in x gonna give you the slope, and we want to be able to gravitate toward the minimum of the function. I want to also introduce you to the concept of feature scaling. What it does is that it will not change the distributions of the data point. However, it's gonna make sure that each feature is going to have a mean of 0 and standard deviation of 1. To be able to do that for each particular features, you will calculate the mean, subtract that mean from the data x and divide it then by standard deviation, and you get the new value for the scaled features. This is an example of how we scale, and we will do that in coding as well. You see that sepal length and petal length for iris flowers has been scaled down to make sure both features will enjoy mean of 0 and deviation of 1. So in terms of distribution, nothing changed. The only thing changed is the presentation of the value. And the benefit of doing that is that the global cost minimum will be easier to be reached via gradient descent, because it's going to be adjusted going until it reaches the global minimum. The field for gradient descent is not shaping round. Due to the fact that we don't normalize and scale the features, it's going to be overshoot easily. When we talk about styles of gradient descent, we have several styles. The first one is batch. In outer line, we take into account all data points at the same time. So if we have million data points, it's not going to be feasible or efficient to take into those type of amount of data points calculation all the time. We want to only adjust the gradient based on a single data point. And we call that a stochastic gradient descent when we only evaluate one data point at a time. There's technique to boost such use of gradient descent via changing the adaptive learning rate, okay? And then also shuffle the data. So adaptive learning rate meaning that you may decrease the learning rate the longer you train the models because you assume that it's reaching toward the global minimum. And if we train only one data point at a time, you see that the sum value has been taken out of the change in the weight factors formula. Shuffle the data will avoid cycling through, and it just helps with training in general. A compromise between batch gradient descent and stochastic gradient descent is mini batch, while instead of taking a look at either one or all, we take a look at a few data points at the same times. So that is all for our concepts. The next part will start with the coding. Great, I speak with you soon.